Okay, I thought I'd just start now and go through the exercises for this week. I want to actually do that regularly, just to make sure we understand that they are important. Chasing assignment marks is extremely important, of course, but it's not everything, because you have a mid-term coming up next week, so we'll talk about next week, after the assignment is behind you. And you have the final exam, and these are extremely important. So the investment that you place in your weekly exercises will more than return you marks in your final total number of marks that you get in the course. And maybe spending time on your exercises is as useful to you even now than polishing your assignment. If your assignment is close to working and you're going to spend another 2 days on it and maybe not make that much difference, you maybe should reconsider how you spend your time. So the assignment is not worth a lot of marks. I suspect that there are going to be a lot of people which will have very poor programs, and some people that have extremely sophisticated programs. And that is not a problem. I don't mind it even, because it's a non-trivial assignment at pushing your programming skills, and it's a lot to ask for in the first few weeks of a course, which I won't call a programming course, it's a data structures and algorithms course. So I'm pushing you hard. If you can do that program easily, you are well and truly on the path to getting a very good result. If it's a struggle, it's good that it's a struggle, it should be a challenge, and realise that by the end of the course you'll look back on it and say, actually it was quite easy, and concentrate on getting those weeklies done. Those weeklies are very important, not only for the midterm, but particularly important for the final examination. I've reorganised the website slightly so that the current week's exercises are at the top, and I've got a directory here at the bottom where I've got the solutions. I want to keep week 3 closed, blocked, till the end of the week, I think, just to give some of you maybe a chance where you're going to give up on the assignment, say, well, you've done enough, it's submitted, and then spend a little bit of time, at least a couple of hours, on the week 3 to finish that off. Even if you pick and choose and just do a couple, it's worth the effort. In week 4, which I've already forgotten, I'll have to look at again, first 2 very simple questions, and one would make an excellent exam question. I'm not going to ask it obviously now because I've asked it here, but it just gives you an array and its starting address of the array, and I ask you the values, what are the values of a certain number of expressions that include the array name and a pointer. So you make a pointer out of it and do something, or what's the value, and you add addresses to it or add numbers to it. So what's an address and what's a value, what's a number, what's an integer? And I think if I asked that question this week, how many people would get all of those right? I think it would only be a very small number. Okay, so it's a very simple question, costs you 2 or 3 minutes, but whatever you do, don't look at the answers, even if you get to the next week and after I've published the answers. Do it first. Because if you look at the answers, you will say, oh, I knew that. And you're lying to yourself. You didn't, but you think you knew it, because it's sort of obvious when you see the answers. Oh, of course. Oh, I know that from now on. But you will not, because I'll give you something slightly different, and you will have no idea, and you'll get them all wrong. Okay, so trying yourself, it'll only take you 2 minutes. It will be some of the best 2 minutes, will probably be the best 2 minutes for you in the course. Because if you can't get that right, you'll have a lot of problems with all the C programming. It's a really simple little test on where you're at in your head. The structure is much easier. It's just I'm trying to obfuscate the program here a little bit by giving you 3 variables, per1, per2, and a pointer. See the person star. And I'm just using the pointer or the data structure names itself, per1 and per2, to populate the data structure. So what is the data structure going to look like as a result of these assignment statements? That's also just 1 minute. I don't think many of you will have a problem with that. Next question is on Cush. Just writing Cush for the linked list quack. So you're going to have to take the quack ADT from the lecture slides, add the Cush. I don't say that, you're just going to have to work it. I do say, yeah, I say you need the quack LL ADT. So you have to cut that, paste it into a directory, add Cush, cut and paste Josephus, and compile the whole lot together and check that it's running okay as a test. Now, the real programming things question is this one here, which is converting a real number, base 10 in other words, decimal number, to binary. That's the first question. Now, I'll give you the algorithm to do it that uses a stack. It involves a push of the remainder and then a division of the base into the number itself, into the decimal number. How many whole times that number goes in, the base goes in. And you do a loop, continually pushing, so you built up your stack, number of elements on the stack are the number of, basically number of digits in a number of binary digits, and then you pop them off, and the popped order will be the correct order. So that will give you, so I'll give you the algorithm here. It's almost as simple to program that as you see it, because you see a while loop, it just more or less tells you what to do. So all you have to do is the housekeeping around it, the main and the usual stuff. And then you can test it. I show you how it works here for the case converting decimal 13 to a binary number. And it starts with 13. The binary number is, of course, well, you divide by 2, the base is 2. You divide 13 by 2, you calculate the remainder of 13 by 2, and the remainder is 1. And so you put then on the stack 13 divided by 2, which is 6, and you do it again. 6 remainder 2 is 0. 6 divided by 2 is 3. Put 3 on the stack. 3 remainder 2, 3% 2 is 1. 3 divided by 2 is 1. Put 1 on the stack, and that 1 is the remainder. And then you divide 1 divided by 2, and that's 0, so you're finished. It's really sweet. Use a stack, not a queue, a stack, of course. So popping yields 1, 1, 0, 1. Done. That program is quite simple to write, and I ask you to use a command line argument. So base 2 of some number, 13 say, will give you 1, 1, 0, 1. And I ask you to make sure there's just one numerical argument, that you don't have 5 arguments, that there is no alphabetic thing, so you don't have 1x or something like that as an argument. It's just got to be a simple decimal number. So your program should behave correctly, should be robust. I'll give you some example. Base 2 of 127 is 11111. And base 2 of 2730 is 101010, etc. Now, the more interesting problem that I had a little bit of fun with, it's simple, but it does make you scratch your head a little bit, and that is now generalize a program which goes to binary, converts a decimal number to binary, into a program that converts from a decimal number into a number of any base between 2 and 16. So base 10 or base 12, base 11, base 8, all permissible. So you have to give it two arguments now in the command line, the decimal number, 13 say, and the base that you want to calculate or express that number, base 2, so it would be base space 13 space 2 would get exactly the same behaviour as the previous exercise. Base space 13 space 3 will show you what 13 is in base 3. So you have two command line arguments, which mean you've got to do a little bit more checking to make sure you get good data. So I'll give you some examples here. The decimal number 2730 in different bases, but something should spring out at you, and that is when you get past base 9, you then, or base 10 in fact, base 10 is of course decimal, so if you ask 2730 in base 10, it comes back with 2730. It does work. But when you go to base 11, you have character digits. Use A, B, C, D, etc., depending on the size of the base. So if I ask you for 2730 in base 16, you see that the answer is A, A, A. Okay, that means it's 2730 is 10 times 16 squared plus 10 times 16 plus 10. If anyone's following me, I'm not sure. A is 10. The first A of the 3 is 16 squared. The second A is 16, and the third A is, if you like, the remainder. So A is 10 times 16 squared plus 10 times 16 plus 10. And I hope that's 2730. That's what my program produced. So it's a fun little program because you realise that when you have numbers on the stack and you can pull them off and you've got to print them, oh, I can't print 10. It's ridiculous. That's not right because I'm working in base 16 or base 12 or base 13 and I need some characters here instead of numbers. Now, it's a really good exercise. I think you'll have some fun with that. And how much, do I have another exercise? I did too, oh yes. And I asked you, for example, to test your program and to tell me what 51966 is in hexadecimal and what 19006 is in duodecimal. If you don't know what duodecimal is, you can Google it. It's all part of the fun that you'll have. I think some of you will really enjoy that exercise. And the next question is quite a simple exercise really, although there are a couple of constraints on it which make it a bit nasty, and that is I want all the prefixes of a string. So the prefixes of the string are, well, anything more than 0, of course 0 is nothing, but if you have the ABC, the prefixes are A, AB, and ABC. Okay, the string itself, take off one, the last letter, take off the second last, take off the third last, etc., all the way until you've got just one character. And so you have all of the prefixes of that string, so you hear for the word programming, all the possibilities. And you are not allowed to use any library functions, no string functions, for example, and you are not permitted to use any arrays at all, except for, of course, argv, which is where you're getting your string from. So you can't process it in the way that you copy it in some fashion using some string function from string.h. You have to work with the string in situ, in the actual command line array argv. You're not allowed to take it out, but that's what it basically means. You are not allowed to take it out. And you must work with pointers. And the really what I call it, the really interested ones, the passionate ones about, will think, oh my goodness, yes, I've got my argv, I know where it starts, and I want the prefix, and I want to actually go, somehow I've got to go to know where it finishes, and then I want to print it, and I want it to stop printing in some kind of loop where I only print up to a point, and then I come back with that point, and then print it again from the start to a point, and then I come back with the point I print to, and then I print from the start to that point, and I come back with the pointer, so I have to have a movable endpoint. That's the kind of thinking you should be doing, and it's just a couple of lines. But it should cost you a little bit of time to get the pointers right. It's a very, very useful exercise. There's not much you can do wrong, in a sense. If you get it working, it will be obvious and simple. But they're the nicest problems. The problems that you have a very simple, clean, elegant, infinitely readable solution that took quite some time to think of. The energy is in the thinking, and the result is sublime, sweetness. Okay, these really big, long, complicated programs, reading data for that assignment is a horrible mess. There's no satisfaction in it. I mean, it works, and sometimes you scratch your head and I wonder if it always works or whether it's going to have some real problems, and I wonder what the test data is going to be and whether I've forgotten something. It's just an unsatisfying process. It's a complicated, messy, difficult to follow. My program as well, I have trouble following my own program. Every time I look at it, I say, what was I doing? Oh, yeah, oh. And it's all got to sort of come back to me. That's not elegant, that's not nice. Little problems like this, you look at them and you instantly can see what it's doing. When you see a good algorithm, in any case, a good program. Okay, so they're the exercises for this week. You should have some fun in there. Now we're moving on. The course moves on. And some of you will probably think, my God, I'm not ready for this. I'm still handling the C, and I'm past that now. I'm on to more interesting things. What do I want to do? Browser. So what we're going to do today, I like this table of contents. It's very primitive on the wiki. It has some funny formatting, but it's nice. When it gets complicated like this, I don't know how far we're going to get today, so I've got to be very careful with the clock. I think I've expanded this in the last couple of days, and I think it was a 3-hour lecture before. So this means it's probably 2 2-hour lectures going to be required. But we'll see. Okay, program analysis. Let's have a look at a couple of the headings. What does it mean when you do it empirically? What is complexity analysis? Linear complexity, polynomial, exponential and factorial, logarithmic complexity, big O notation. I go to big omega. 9 is interesting. You'll see a little video, which you may or may not think interesting. It's only 6 minutes. How good are the bounds is a bit of philosophy. Examples of different algorithmic complexities. I show you some real world and mathematical algorithms for different complexities. Talk a bit about log n versus linear. Then I, believe it or not, go into recursion. I'm hoping you know what recursion is. I did have a 1.5 hour lecture on recursion, which I haven't given you. It's not relevant to the assignment, and the assignment mallets and standard input, these were much higher priority. So I've sort of skipped that. So I'm hoping Eric's done enough recursion with you that you actually know the basic concepts. But I did have a really interesting 1 hour lecture. Well, basic, but interesting. So we'll go straight into it here, and if it turns out that you're hopeless with recursion, or you have a lot of trouble with it, struggling, you may have to resurrect that lecture. So we look at Fibonacci, which I'm sure you've done, and Hanoi, which you've probably also done, and also Ackermann's function. These are 3 very, very, very well-known functions, algorithms, but I look at it from an algorithmic point of view of what's going on, not so much the implementation. implementation in some sense boring. You would have just implemented and got something working using some, if you like, strategy, but I'm looking underneath the bonnet of the engine to see what's actually happening in each case and what is analysing the program, I suppose you could say, simple as that. Okay, now, did I have something above that? Yes, I did. Program analysis. Program may execute for a small n. This first line almost sums up an awful lot of what the... Well, keep coming back to this issue. For small n, you can run your program, but what do you know about the performance when you increase n, when n gets bigger and bigger and bigger? What do you know about asymptotic behaviour? Does it scale? Scalability refers to the space it occupies, the amount of memory, and also, of course, the time it takes, the execution time. What do you know about both? Now, I will come back to this point a number of times. This concept of does it scale, of course, it's a question you only have if you are going to scale it up. If you are happy with little values of n, then complexity is a pointless exercise. Simple as that. Don't do it. No analysis necessary. If your n is never going to be bigger than 3, now n is some input variable and it's the length of an array or the size of something. If it's small, complexity analysis is a pointless exercise. Complexity analysis is only for large programs. Large in the sense of programs that consume a huge amount of time or a huge amount of space. The father of complexity analysis is Donald Knuth, still alive, still at Stanford, an emeritus professor there, the professor of the art of programming, I think is his title, actually said computer programming, that's the name of his 3-volume encyclopedia of algorithms. An amazing piece of work. Even today, many people swear by it, and that is there. That's where they go for all the algorithmic questions. It tells you anything that you want to know about algorithms. A complexity analysis is a part of the design process. The idea is you've got to get your design right first. And then, in the implementation, you worry about the optimization. Don't let optimization infiltrate, become part of, sabotage even, the design. The design is about getting the pieces of system together, the basic algorithm, down to what it should be, getting it right. That may mean, for example, choosing between recursion and iteration, or dynamic programming, or some other technique. What most people do when they write a program and they want to see and test it to see how it performs, you write your program, you run it with inputs of varying size, you measure the actual running time with your watch or using time on the system, and then you plot the results and you say, okay, I can see where it's going, I can now predict that is with input size roughly 100, and I know exactly what the range of execution times will be because I've run it so many times. So with 150 and 200, I can predict how long it's going to take. Now that is sort of useful, but it's amazing how wrong you could be, which is what we go on to now. The limitations of this is you must code the algorithm in the first place, but I did say it was designed. The complexity analysis and program analysis is part of the design. Here I've got a program that's working, so really what I'm doing now is I'm writing it and crossing my fingers, and then I'm running it and crossing my toes too, and hoping that it performs okay, because if it's not, what am I going to do then? Go back to the design and think of a brand new algorithm, throw the program away, and say, well, okay, that's not the right way of doing it. I have to think of something else. That is terribly wasteful. All your time, all the testing, everything's gone into it. Basically, you have to rethink the whole process. So the results depend on the input we give it. Well, have we tested it properly? How much input are you going to give it? If you want to compare it with other algorithms and say, well, is this going to perform like another implementation from somewhere else? You try to generalize it, get an understanding of where your system, how it compares with others, so that you can also predict how it's going to go, because you know others have been used in a certain way to a certain degree or certain size of input. Will yours go the same way? Well, you need to have some kind of basic platform that you're working from, same software, same compiler, same hardware, to get a good sense of whether your algorithm is better or worse than somebody else's, whether it's going to be faster or slower. And that gets hard to do when you're talking about remote implementations. So how do you know when the input is big enough? Can you know how big the input's going to be? Will it have to be very big, or maybe you don't need to worry about anything because it's never going to be big? If it could be arbitrarily large, like a board in the assignment, how big is big? I've deliberately tried to avoid that whole question. It's arbitrary. If I find something in your program that limits it, I'm going to give your program one size board bigger. So whatever you give me, I'll make it bigger and break your program. Okay, it's what I enjoy doing. Break your program. Makes marking very easy. So if a test, and the great fear that every programmer has, of course, is you run your program, you set it going, and it doesn't come back. What's it doing? Is it in a loop? Is it just going to take another minute or 5 seconds? Can I have a cup of coffee? Should I wait? Or should I go and get my coffee? And you come back and after your coffee and still not, what do I do? Do I kill it? Because I waited this long. Should I? I don't know how many times I've had this dilemma. What do I do? Is it wrong? Or am I right and just being impatient? Is this acceptable? What's going on? What do I do? So here is straight away into, I see here a number of pictures of graphs of performance, and you see it's not as clear on my screen, it's not as clear as what you've got up there. See the red one, the log, the square root, the green, then the dark blue, which is linear, then the purple one is quadratic, and then the yellow one is cubic, and the turquoise, I call that turquoise, is exponential to the input. That's exponential. Now, you've got an algorithm, a program, a number of programs, and you're comparing them, and one of the programs you want to use. You don't know which is going to be the fastest. So you've got all these programs that have different colours. Forget obviously the computational performance. We just got different colours, different colour programs. A yellow program, a red program, and we have to choose between them. That is your job as a test engineer, software engineer. You have to choose the best program. So the first thing you do is test it. Well, I won't try test 0 and 1, I'll try straight off, give it n equals 5 or something. N equals 5, I think. And see what it does. And now if you look at n equals 5, here, that's that first measure there, first value, 5. And you see that turquoise is bloody good. It flies. And that yellow is pretty good. And the red, that is terrible. It runs really bad. It hobbles along. It is maybe 10 times, 20 times slower. Now, the first thought is, forget the red. That red program, whoever programmed that, shouldn't be a programmer, is an idiot. Even for n equals 5, he is a moron. He couldn't get the program to perform. So red is moronic. Stupid. Well, not sure, but your friend, your colleague says, let's try it for n equals 10 just to make sure. For n equals 10, so we use the next step up, we get some new results, and yellow still looks pretty good. Red is still abysmal. It's twice as slow. Left-hand side is the time. And turquoise is now even worse than red. Sorry, have I said that right? Turquoise is got worse than red. So turquoise was an absolute flyer at the start, but when it comes to this next data, it's died. It's got slower even than yellow. No. Don't know what's wrong with turquoise. It's got tired. What its problem is it looks like, based on that, I think yellow now. First off, I thought turquoise, but maybe it's yellow. And you can see what the future behaviour will be. You would be an idiot not to take the red one. Imagine waiting for the turquoise one when you give it data 20 or 25. You will wait forever. Well, maybe an exaggeration, but in any case, billions of years for that program to finish. An exponential program for even 25, n equals 25, would take billions of years. Now, you think I might be exaggerating? I'm not. No, I will show you later how you can compute this. Why you can work out how long it's going to take, or how you can work it out. So, based on this evidence, you would be very wrong, still, in the choice that you would make, yellow. Knowing what happens asymptotically, which algorithm should you have picked? Well, of course, red. Clearly, red is much faster than yellow, and turquoise will take forever. Turquoise is just not in the picture. It just goes right up in terms of time. Now, yellow is bad, and red is perfectly doable. Actually, it's almost flat. It's almost constant. So you would only barely have time to have a cup of coffee if you up the size of the input. With yellow, you could probably go on holidays for a week and come back. We're talking about a couple of hours and a few weeks, that kind of difference. Okay, so based on data, empirical data, just run it and have a look and take the risk, if you like. Choose one that you think is fast, is highly risk-prone. It can easily go wrong. You could be very wrong. So in a complexity analysis, there are three things that are happening. First and foremost, complexity analysis, and a complexity analysis is about abstraction. And that's not something you'll find in many websites or in many articles. I see it as an abstract measure of the performance. Because the thing that you really do, and you're going to see that here tonight, is you throw away everything that doesn't contribute to its ultimate performance, to the actual serious performance. If it's going to take billions of years to run, you want to know about those billions of years. You don't want to know about things in the program which will contribute a few seconds, or a few hours, or a few days, or a few weeks, or a few months even. Billions of years is billions of years. That's a disaster. The details you want to get rid of. You can only analyse something, do a complexity analysis of something, when you simplify it down to the dominant behaviour, the term in the expression that expresses its performance. You want the dominant term. That's all you want. The rest is irrelevant. So, how do you do that? And what does it mean when you've done it exactly? The next thing is, of course, it has to be asymptotic. If you're not interested, I'll come back to this point again, not interested in large N, do something else. Go to the next problem. This is not an interesting thing to do, complexity. We're talking about programs, applications where you can have arbitrary large input. And anything that's serious, to be honest, will have that. Serious. If you're writing a sort program, for example, you don't want to say, well, I can only sort up to 5,000 elements, and after that you do something, I go away. I don't want to know about you. Well, 5,000, the customer would say, why 5,000? Well, okay, 10,000 then. No more. Oh, I might have 15,000. I have a few people in my club. Okay, 15, no more. No, maybe if I grow, I'll be 20,000. What happens if I go to 100,000? All right, look, how many are you going to need? Well, I don't know, I just want a lot. Asymptotic. Normal applications, sorting and searching certainly, almost always require not necessarily infinite, but arbitrarily large. That's one reason I gave you this assignment, so that you grapple with arbitrarily large, but not necessarily at the complexity level, which is what we're talking about here. You are dealing with it at the programming level. Okay, and the third point is we get a classification, a simple classification, and ultimately that is what we do as scientists, computer scientists. We are interested in classifying. Biologists classify animals and plants in species. They don't just have a name for everything and say, well, okay, that's a that, and that's a that, and that's a that, and that's the end of the story. No, they have everything organised in families and subspecies and sub-subspecies. These all have characteristics. Huge effort goes into classification. That is what science is about, classification. All scientists classify, try to structure, order, and understand the relationship between these classifications. What binds things together and what separates them, what makes them different, and what is the relationships. Exactly what we do in algorithms. We try to understand which algorithms are actually the same in terms of performance, memory or time, and which ones are completely different. So if you have an exponential algorithm, you want to know that. You don't really care what it does, but is it exponential? Then you know what it's going to do and not do. And not do is probably it won't finish. If you know that beforehand, it's exponential, that will affect your design in a big, big way. If you know it's going to be linear or quadratic, and then cubic, maybe, is it doable? How big will my n get? Can I get the bet? Can I get it a bit better than quadratic? Maybe. Can I get it to power 1.5 instead of power 2? These are the issues then you come across and you think, well, how am I going to restructure it, change it to make it a better, a more efficient algorithm? So we have the three prongs, the three bases, three legs that we're standing on. There's abstraction, asymptotic behaviour, and classification. Now, let's get serious. Let's look at a little program. And here we have our little linear search program, which is looking for, and in a sense, as a result of, we've now put behind us the programming part of the course, where I forbid arrays and forbid all sorts of things and tell you you've got to do this or that. Now I'm just interested in algorithms here. I'm not interested in how you've implemented. I don't really even care what language you're using, but of course we'll use C. So for example, up there you see the parameters there, int A, and I could have made that a pointer and I could change it to make it look a bit different, I suppose. I've got a thing called key. Don't like using words like that as variables in C, but okay, it's a key I want to look for, and I have the size of the array n. 3 parameters to this function, and I assume that I haven't found it. That will be the value that's returned. Found equals -1 means I haven't found it, and I go through one at a time looking for this particular key, some value in the array. And as long as I haven't found it, I'll keep looping around, and if I have found it, the index of that value I put into found, and then as long as, and if I found it, I then jump out, I hope. Yes, I do jump out. I jump out when found is not equal to -1, so I finish the loop, and the return value is either -1 or the index of the found value. That shouldn't test you too much as programmers. Now, what's the worst case behaviour here? The key's not there. Then it's going to go from start to end looking for that key. How long will that take? Well, what's the worst case behaviour per line? Well, line 2 happens once. Line 3, which is the for loop, happens n+1 times. 0 to n, what did I call it, less than or equal, what if I can't, well, yeah, less than n, so to n-1 plus the next term, of course, so we have n plus 1, 0 to n-1, there's n plus 1 is n plus 1. So line 3 is n+1 times, then line, in the loop itself will run the n times, so line 4 is n times. Line 5 doesn't get done at all because we don't find it in the worst case, 0. And line 8 is the return, and that's found. So the total is However long it takes line 2 is some constant. There's no variable n in line 2. There's no algorithm in line 2. It's just do it. It takes some time, whether it's a nanosecond or a millisecond or a year. It's just a fixed amount of time. So that's a constant in terms of time. That's line 2. And, well, line 3 is done n plus 1 times. We saw that. And line 4 is n times, and line 8 is 1 time, just a constant. Now, if we just group them together, we see a constant of line 3 plus line 4 times n plus a bunch of constants. So the total is some constant times n plus another constant. Now, as we do in complexity analysis, I throw away the constant and I say that algorithm is linear. Okay, the constants we can ignore. Hence the worst case execution time is proportional to n. It is classified as a linear algorithm. Being linear, we can predict that if we increase the input, we double the input, it'll double the time. If we triple the input, it'll triple the time. It's completely predictable. We know what we've got. We can predict how long it's going to take. You can tell the client, if you give it 100,000, you know how long it took for 10,000. If you give it the number n equals 100,000, you can tell him exactly how long he's going to wait. And if he's not happy with that, then you're going to say, well, you should have told me at the start that you wanted a faster program, but no, I wouldn't give you a linear search. I would have given you something faster, like a binary search. And that will cost you more money, because it was your mistake. You didn't tell me. Okay, so you give the algorithm that they order, in a sense, depending on what their requirements are. Now, we go to polynomial complexity, more serious algorithms. Most algorithms are not linear. Linear search is probably the most popular algorithm in the world, and is also probably the only one that you'd naturally normally come across. So if you have an expression of the execution profile, as we call it, and you do the same calculation, usually you have a double loop, which is bound, each loop is bound by n, the input size. When you have a double loop, you'll have an n squared program, performance program. You'll get something of the form constant times n squared plus a constant times n plus a constant, all different constants, of course. And, well, we can also have cubic, you can have quartic, and you can have quintic, and keep on going. They can be any size. So you get the expression which determines the performance simply by counting the number of times a particular line of code is executed. In all the other versions of this course, from other lecturers from the last goodness knows how many years, I have noticed they all go to this pseudo programming. Now, I don't like pseudo programming, and I have seen discussions on the web about how much time a particular instruction in pseudocode costs, and it's somewhere between English and C, the pseudocode. And it's a way, or sort of an algorithmic way of describing something, a process, a program or a thing, and you have to work out how many actual operations. So one operation, there could be an addition, and then an indirection, which could be a pointer, which is another operation. So one operation, one instruction, one line could be 3 or 4 things, could do 3 or 4 things. And when you get a for loop, and it's a bit complicated, wow, just counting the number of operations in the for loop that are sort of behind the scenes, that are sort of part of the pseudo language, is a real nightmare. And you could argue, well, should I be counting that as 2 operations, or is that just 1? When I increment an address, do I access the address? Is that an operation, or is it just the addition of 1 to the, what is the number of operations? You can get into a real muddle. And I stay away from that. I don't think adding another language, pseudo or not, is certainly one that's vague, related to any natural language. I think it's crazy. All that we're interested in is complexity, is abstracting the performance, getting the main features of the performance, and C does that fine if you just count lines. Some lines, of course, can be pretty heavy, but the thing that is important to remember, and I haven't seen an exception to this, is that a line of code, no matter what it is must be a constant in terms of performance. And constants do not affect complexity. That is what complexity is. It is abstract. It doesn't get affected by details such as constants. It even goes further than that, and here you see, for example, any of the cubic and quartic and quintic and all the big n power of n performance or execution profiles, they're all called polynomials. Our polynomial algorithm will be quadratic or whatever, cubic or whatever. But you've got to be careful, these things get pretty subtle. N to the 1.0000000000001 is polynomial. It will have worse performance than linear. Linear was the linear search. It's just 1. So n to the 1, if you like. When that 1 is a teeny weeny bit bigger than 1, or when the power is a bit bigger than 1, it will ultimately give you poor performance. But of course, we're now talking about the more decimal places you have in that power, the longer it will take for that polynomial behaviour to manifest itself. And if you're really going to give it values of billions, well, it could become important, but anything less than that, it probably won't be, you won't be able to see the difference between polynomial with such a tiny or such a power, 1.0000001, and linear. It won't be, you won't be able to tell the difference. So, but the dominant term is really important. So if you have a quadratic with a linear term and constant, you throw the constant, throw away the linear term. Okay, too wild. You also throw away the linear term. And why can you do that? Well, when n equals 100, then of course the linear term, well, when the term n is 10, then n squared, if it's a quadratic, is 100. 100, 10, 110, that's probably a significant difference. But if n gets big, and we're talking about whatever number I've got there, 100,000, and the difference between 100,000 and 100,000 squared, which is 10 billion. Now, 10 billion, if you add in the linear term, you get 10 billion plus 100,000. Well, to be honest, if you're going to be waiting the rest of your life for a program to finish, because the end size of the input is 10 billion, 100,000 is small change. It doesn't make any difference anymore. You'll be well and truly dead by the time the program finishes. That 100,000 is not going to become important. 10 billion is 10 billion, and the rest is small change. So the dominant behaviour is all that you need. You don't need the detail, the small stuff. Asymptotically, that is, as n gets very large, we see that n squared plus n converges to n. They just get n squared. They get closer and closer. In general, in linear algorithms, we ignore constant factors. In quadratic algorithms, we ignore linear and constant factors. In cubic, we ignore the quadratic terms, etc. Now, that brings us to the next class. We've had linear. Let's talk a little bit about polynomial. Now the exponential. These are the really big ones, the serious ones. These are the more interesting problems in many cases. The size of the space usually doubles, increases by a multiplicative factor as n increases linearly. So if you add 1 to n, you go to n plus 1, the size of the space can double. Now that double means 2 times. So we have a multiplicative factor, and that is characteristic of exponential. So for example, you are computing all the subsets of an alphabet of n characters. So if you have n characters, or n numbers, or n A, B, C, D, E, F, and you want to have every possible subset of that A, B, C, D, E, F, every time you add one more character, the number of subsets just goes through the roof. It has, and the size of the state space is that actually the number of things you've got to generate determines the performance. If you've got to generate 3 million subsets for some value of n, that's going to take you a lot longer than generating 300. So the 3 million is the thing that determines the performance. So the size of the output, if you like, is the thing that actually determines the complexity. The execution profile is dominated by the term C to the n. So in these problems, you can characterise them by not n to some constant, n to squared, n cubed, n to the fourth, to the fifth, etc. They're the polynomial algorithms. We turn it on its head, and we have C, the variable that changes becomes the power. So it's C to the n. Now this is the way you characterise these exponential algorithms. It just turns the C and the n upside down. Factorial is, what do I say there, C and C could be any exponential constant, for example, 2.7, 2, 10, anything. So the C underneath the n, you think, surely it's important. No, it isn't. It makes no difference. Most problems are 2 to some power, and they're horrible, and if it's 2.7, in other words, E, or 3, or 10, or 20, they're just as horrible. They're an infinite time or intractable problem that can't be solved in finite time, basically, or in our lifetime, is intractable. Whether it's a 2 or 3 or 4 base, it doesn't matter. Now, then you have factorial problems, and the execution profile is dominated by n factorial. And a good example of that kind of problem is just the sliding tile puzzle. The sliding tile puzzle is a nightmare, algorithmically speaking. It is so easy to understand that you all will know or feel in your bones, I hope. Well, maybe not yet. No, you don't, because you're only working with solvability, and you may still think it's quite trivial. Very soon, when we go into breadth first and depth first search algorithms and heuristic algorithms, and you see the size of the space of solutions, how many solutions are possible, you'll be quite shocked. N factorial looks so simple, but when n gets even slightly big to 10, 15 and 20, it is a monumentally large number, astronomically large. So you cannot achieve any big N with any factorial problem such as sliding tile. So, and I'm not sure whether I said this somewhere in all the notes and things, but to the reality is that a puzzle, sliding tile puzzle, bigger than 5 by 5 forget it, it's undoable. 5 by 5. Now some of you are testing 500 by 500. It's in such a fantasy world that it is impossible. You'll never have a 500 by 500 board. 5 by 5 is bad news. 3 by 3 is semi-doable. 4 by 4 is already horrible. 5 by 5 is the nightmare stuff. 6 by 6, nobody even tries. It's ridiculous. 36 tiles. 35 tiles with a blank. It's undoable. Okay, but you'll learn that, you'll see that later on. Then we come back, having done exponential, I go back to logarithmic, where these are the problems that work the opposite way. They tend to have the divide and conquer. And when you try to solve something for n, you break it up into two problems which halve the size. When you go from n to n plus 1 in exponential, you tend to double the size of the problem. When you go from 2 by 2 to 3 by 3 to 4 by 4, in the sliding tile puzzle, the number of solutions, the number of possible moves that you can make, just goes vroom, straight up. Incredibly steep. When you have logarithmic, it works the other way around. You halve the size of the problem by breaking up the problem in a divide and conquer. You break it up into two halves where you can actually work, and the two halves are in themselves much simpler. You halve the size of the problem, which can have a major computational effect. Then you halve it again. In the end, you've only got one to work on, and then you kind of combine them again, and the total is incredibly fast. Because, and that's the thing that you've got to get your head around, how can you visualize this? Well, the way I think of it always is, when you have a problem, and then you break it up, and you have two problems, and then you break it up, and you have 4, and you break it up, and you have 8, and then you have 16, if that's it, then you go back up again. The height of the breaking up, which can be 3 or 4 or 5 deep or 6 deep, is much smaller than the width, which is the number of n, size of n. It's the square root. And that height is going to determine your complexity. And that will be logarithmic in the value of n. We'll get to that. And this is a bit of a side. Sometimes you see ln, and sometimes you see lg, and sometimes you see log, and sometimes it's base e, sometimes it's natural, sometimes it's binary logs, and it all does not matter. If you like, the bottom there, which says conversion, log n equals log e times log n in its natural and binary versions is just a constant 1.44 difference. So you can get one to the other, you divide or multiply by some constant, so it doesn't matter. I tend to write just log, and whether it's to the base 2 log, base 10 log, or base 3, whatever, 2.7, whatever. Anything you like is okay. Any constant you like. So just the same reason you can throw away constants in quadratic and any other complexity analysis, you can forget the base of the logarithm. The fact that it's logarithm says everything, not the base. Now, let's have a look at the computational complexity. And believe it or not, there are two interesting units of measure here. The first interesting unit of measure is a nanosecond. That's 10 to the minus 9 seconds. 10 to the minus 9. To get to a millisecond, that's 10 to the 1,000th of a second. A million nanoseconds is a millisecond. A million. Sounds like a lot, but times a nanosecond, it's still not much. You can't blink in 1,000th of a second. It takes you a lot longer. So it's very, very fast. So a nanosecond is incredibly fast. The other unit of measurement that we need here is what I call the AOU. Have I got it there? No, not yet. AOU, the age of universe. Age of universe is an important measure in the performance of algorithms. And you sort of say, well, this is crazy stuff now. On one hand, I've got nanosecond. It's ridiculous. It's instant. And now I'm talking about the age of the universe. When did this so-called Big Bang happen? When did it all start? Billions and billions of years ago. That's also a fixed time that interests me. Now, if I'm interested in performance, and I assume that an algorithm for n equals 1 takes 1 nanosecond. That's a baseline. I'm just trying to get a sense of what it is if I have a quadratic algorithm or a cubic or quintic or an exponential or a factorial even. If I have any particular algorithm and I know for n equals 1 it takes 1 nanosecond, what would it take if it's n equals 2, maybe 5, or n equals 10? If I increase the size of n by 10, what's it do to the computation time? So you see, I'll give you an example to give you a feeling. If it's a quadratic algorithm and it takes 1 nanosecond for n equals 1, then for n equals 10, it takes 10 nanoseconds. That's not that hard. Linear means it takes proportional at the same time. And if I up it to 50, n equals 50, then it takes 50 nanoseconds. And 100, like 100 nanoseconds. I don't know what I'm doing tonight. And so on. So we get a sense now. Gee, the people who are going to listen to this are going to hate me. Okay, now we can start to get a feeling for what's going on here. Now we have log algorithm, we have a linear algorithm, n log n, polynomial, exponential, factorial, and just what I call truly horrible. and n equals 10. So we've gone to 10 times the input from 1 nanosecond with a log algorithm, which goes from 1 nanosecond. When you put n equals 10, it is 3 nanoseconds. Well, okay. Now with linear, we saw that before, 10 nanoseconds, 10 times 1 nanosecond. With n log n, 33 nanoseconds. With polynomial, n squared I'm taking as my baseline, if you like. We're not worrying about cubics here, and etc. So we just take one polynomial, n squared. And we see, of course, n squared is n squared. N is now 10, 1 nanosecond for 1, so 10 squared is 100, so it's going to take 100 nanoseconds. It's not hard. Exponential, well, it's now 2 to the 10, not n to the 2, it's 2 to the n, and that is 1024. And factorial is 3 million nanoseconds. Oh, that's making me a bit nervous, but we did hear before, 1 million nanoseconds is still a microsecond. 10 to the minus 3, that's a millisecond, micro is 10 to the minus 6. A millisecond, so that's still very, very fast. So no problems. And even the truly horrible is 10 million nanoseconds. But you start to get used to the numbers a little bit. Now, if I go to 50, you can see 6 nanoseconds for the log n. The polynomial is up to 2,500. The exponential will take you 13 days. That's the program that starts when n equals 1 nanosecond. 1 nanosecond. You give it n equals 50 and you might as well go to Hawaii for a week, enjoy yourself, get married, and come back and your program may be finished. Have a nice honeymoon too. Okay, that's what we're talking about here. If you can predict that, just time it. Start it off and off you go to the airport. Okay, there's no problem there at all. It'll work out well. Come back and it's finished. Now, if you take a factorial with n is 50, now remember, the puzzle was factorial. Now, the amount of time you need to run the program for n equals 50 is 10 to the 40, so that's 40 zeros, times the age of the universe. The age of the universe is roughly 14 billion years. So, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, etc. 40 0 times 14 billion. That's how long, in years, that's how long it will take. So when you want to think of a big number, just think of, and you can tell your loved ones this, if you want to think of a really big number, just think of factorial algorithms with n equals 50. Well, for that matter, why not go to n equals 100? And what can I say? The answer is gasp. It just mind-bogglingly, you just can't even imagine. The number of zeros is horrendous, let alone the computation. What you're talking about here is times 14 billion and in years too. These are just monumental numbers. Now, these super exponential algorithms, you could call it that, really are super horrible. The truly horrible, I've got there is n to the n, but there's actually even worse. By the way, you can actually get, well, to think about it. You don't have to be brilliant now to be really horrible. N to the n. Well, let's make it a bit worse. What would be worse than n to the n? Who's the horriblest person here? Who thought of n to the n to the n? No one. Or n to the 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 n. Now these are just numbers you can't even imagine they're so big. We're talking about numbers where the number of particles in the planet Earth, number of neutrons on the planet Earth, of everything, the planet, the core, everything. I'd love to throw this thing away. Can't do that, can I? So, okay, the numbers are massive. Now look at log n. 13 nanoseconds. I mean, you can't, your finger hasn't even left the key, and it's finished. And we're comparing that with age of the universe. So you can see the scale of the differences here. When we talk about complexity, we are serious. We mean serious business. It's an extremely important thing. If you can talk complexity, you have a godlike ability to predict the future, to say what's impossible and what's doable and what's easy. It brings a huge insight into problem solving. Observation, anything lower than polynomial is good. Polynomial can be okay if n doesn't get too big. And exponential and factorial are just ridiculous for anything bigger than 10. It is rare to find practical exponential algorithms, but they do exist. The above is a theoretical worst case behaviour as well. I'm talking about worst case behaviour for n. Now, if there is some property with the values you've been getting, for example, if you're sorting and the n is the size of the array that you have to sort, of course, those n numbers, if they're completely sorted already, any sort algorithm that's worth anything would immediately do a linear search and say, well, this one's right, this one's right. Oh, if they're all in the right order, I can do that in linear time. Whereas a normal algorithm, most basic algorithms, are n squared. It will take a lot longer. It's not going to be comparing all the possible combinations to get, well, okay, after a week, they're all okay. Oh, well, they were all okay at the start. It didn't need to do all that work. It just could have walked right through and checked it. So the nature of the input can be important. Are we talking about the worst case, best case, or average case? Well, the best case can be very, very, very much faster than the worst case, but we need to consider the worst case, of course. Big O, used to bound the worst case behaviour for given input n. It's asymptotic. It can be used for space, and you often do see in serious algorithmic analyses a particular algorithm. I'll tell you the big O, the complexity of the memory and of the time, because sometimes there's a trade-off. If you take more memory, you can improve the time. And if you haven't got much memory, then you're going to have to add to the time. That kind of dilemma you could face. Now, best case and worst case with sorting, the one sorting algorithm, the best case can be purely linear, can fly, and in the worst case, if it's pretty unsorted or even reverse sorted, it could cost you quadratic time. Generally, the complexity that interests scientists, computer scientists, is the worst case complexity. So what you're looking for is a bound on the worst possible input for the best possible algorithm using some kind of strategy. So if you're using recursion, for example, what's the best possible algorithm you can think of and the worst input, and what is the bound on that behaviour in the execution time. A function, now here's where the basis of big O notation, the measure of complexity, is in this graph. Here we see represented the exponential. I should call it there e to the n. I should have just called it c to the n. The e is, of course, was that an e or was it a c? No, it looks like it may actually be a c. Can't even see here. Doesn't matter. C to the n as being the worst case here, and then we have cubic and quadratic, and we have our red line curve is the actual performance. Now, because we're interested in asymptotics, we're interested in a bound on the red line past some point. We're not interested in little n. We saw that with the black picture I showed you at the start, where for little n, we got weird things happening, like the exponential algorithm was really fast for little n. That completely contradicts everything I've said. When you get to anything decent with an exponential algorithm, you could wait for the rest of your life easily for the program to finish. Here we are trying to abstract that out. It's asymptotic, which means we want big N. So we want a bound on the red line, a bound on the actual performance, which we can prove. If it bounds the real performance, we know that no matter what we do to that performance of that algorithm, it'll always be underneath, in this case, CGN, some other abstract function which is a lot simpler than the actual behaviour of the program. The behaviour of the program, we don't have a closed form, we just have a program. All we can do is measure the speed of every line, or number of times every line of code is executed. Now, we come out of that with some kind of formula, quadratic or whatever, linear, and with that we say, okay, that's the formula we've got from the running of the program, or from our simulation of running the program. In our head we execute it and count up the number of lines, which is a function of n. Now we try to create in our head, or think of some function which will bound it, which will be the ceiling to that behaviour of that program. And that now is the big O notation, where we provide a function class. A class where we know our program will always be under. So that CGN is a set, which we're going to get onto very shortly. So we ignore the constants. An algorithm with asymptotic runtime, for example, if our function, the red line, Tn equals 100n squared, it's going to be faster than an algorithm which is n cubed for any value n greater than 100. So a quadratic will always be faster than a cubic, eventually. When we have 100 n squared and we have n cubed with no constant, or constant 1, you think, well, 100 n squared, that really does, it gets handicapped at the start. It looks like it's slow. If you don't know that it's 100 n squared, you see the program is going, gee whiz, that runs terrible. I might take this other program. Well, if you could do a complexity analysis and see that it's 100 n squared, you may change your mind if you know that n's going to get big. Because n squared will kill n cubed any day of the week, eventually, and in a big way. So it's important to know what the power of the n is, not what the constant is out front. Including constants in big O notation is pointless. There will always be a point n naught that makes one complexity larger than the other. That's what complexity analysis is about. OGN, the class which is of algorithms which are bound above by Gn, is a set because there are actually an infinite number of functions Gn that make this true. Because, and this is a bit strange, you actually think about this, that when you have your wiggly red line and then you have a G which is above it, which sits on it and actually is the ceiling, it's the thing that bounds it. Okay, well, Gn plus a bit more, G plus n in some sense, G plus with a sort of power, that's also above it. In fact, G squared n will certainly be above it because that's even bigger, and G cubed. And in fact, exponential and factorial, they're all bigger. They're all ceilings. N factorial is a terrible, terrible, terrible ceiling. These bigger classes are terrible ceilings because they're way, way bigger, but they are ceilings. So you can say there is an infinite number of G's which satisfy it, but we want the tightest. And that's understood, but you don't necessarily get it. It's no law that says that it really is tight. We'll get to this shortly. So if, for example, consider Tn, Tn equals 2n. The function is 2n. We could say Gn equals 3n. So the ceiling on 2n, now 2n, where am I getting that from? I'm just counting lines of code that are being executed in loops and things. And I'm coming up with 2n. Now you can say the ceiling on that is some mathematical equation called Gn equals n 3n. Okay, that's the mathematical, our ceiling now. So t of 2n, this is our function, is going to be in the big O class 3n. Well, we get rid of the 3, we don't need that, so it's in the linear class. So at some point, you could, that n class order, the big O class of n will be bigger than, or will be the same as the function that you're trying to model. Consider n squared, 2n squared plus 7n plus minus 10. That's in the n squared, the quadratic big O class, because 2n squared plus 7n minus 10 is less than 3n squared for n greater than 5. Go asymptotically, you find that their ceiling will just be 3n squared. But technically, it's also n cubed and n to the fourth, etc. Because they're all just bigger functions. It's just a question of how tight you want to be. We are interested in the tightest asymptotic upper bound. Now, a slight deviation, there's some confusion, there's a lot of confusion actually between what is order 1, I haven't mentioned it, but I thought now I'll bring it in. What is order 1? Now I had order n squared, and I've had order c squared, or e squared, or e to the n, sorry, not e squared, e to the n, or n to the 2, or n to the 3. I've heard all that stuff, and n factorial, but what about, can you have 1? Can you have a constant? Well, yes, you certainly can. You can have a program that performs as order 1, big O1. Now, that algorithm, for example, here's an algorithm here. If n is even, then even n equals the number. Otherwise, you add it to itself. You double it. So you always get an even number this way. If it's not even, you add the number to itself, and you'll go get an even number. So this algorithm has variable performance. Depending on the number you give it, it'll either be doing one operation, which is it's got to check whether it's even or not, and if it's not even, it's got to do an addition. So it's a second operation. So depending on whether it's even or not, it'll do 1 or 2 operations. Now, that 1 or 2 operations mean it's easy to say, well, the big O class that bounds it, that is the ceiling to its behaviour, is a constant. Some C is all that you need, and it'll always be under. C equals 3 will do it. So under 3, 1 and 2 will always be under 3, so that is an absolute ceiling. That's not the same thing as saying that the algorithm is constant time. Constant time is not a big O class. Constant time is saying literally it takes constant time. That algorithm doesn't take constant time, sometimes 1 operation, sometimes 2. If it was an important, it was very difficult to do. 1 operation can cost 1 day, and 2 operations cost you 2 days. Some weird algorithm. Then, of course, then you must know which one is it going to be, because it can make a big difference to you. So in that case, you've got in this case, with this even, we don't have a constant time algorithm. So the access to an element of arrays. So what are examples of constant time algorithm? The algorithm to extract an element of an array. It doesn't make any difference where in the array you are, or even how big the array is. In theory, you just go to it. Just the value, boom, you're there. How long does it take you to add an element to a stack, or take an element off a stack? It's a constant time. It always takes you the same amount, no matter what the depth of the stack is or what the value you're putting on the stack. It's a constant time. So O1 is weaker, which means that a constant time is always O1, but O1 is not necessarily constant time, and this even function is an example where the two are different. Okay. Thinking that that is as bad as it's going to get, I'm now going to introduce the big omega instead of the big O. And because the big O was the ceiling, the big O was the ceiling, the big omega is now going to be the floor. It's the thing that underbounds it or supports it. It's always less than that wriggly red line that we had before. We're trying to now sandwich our behaviour, or the behaviour of the program. We're trying to get an estimate of a mathematical function. We're trying to get a mathematical function which bounds it from above and bounds it from below. It's still asymptotic. Now, so here's the definition. Algorithm is omega gn if there exists some constant c and a constant n0 that Tn is always greater than or equal to c of Gn for n greater than some starting point which is going to be big, presumably. So we have two bounds now, the omega underneath and the big O above. And not so interesting facts is what we really want. Why are we sandwiching here our function, T of n? Well, we're trying to get a handle on its performance. So if you have a upper limit and a lower limit which are in the same class, big O class in effect, the omega and the big O are the same, then you know exactly the best and worst case behaviour. It's extremely predictable. But if your big O ceiling is quite high, so it could be quadratic, but your omega is quite low, constant even, that's a big gap. What is it now? Linear? Is it n log n? Is it log n maybe? You know, it's close to constant. Where is it? It's too big a range. So the difference between the omega and the big O is really important. It gives you the upper and lower bounds on the performance. And the worst possible thing that you could have is if you have big O being factorial and omega being constant. Basically, that's telling you that the program is going to take somewhere in between 1 nanosecond and goodness knows how many lives of the universe. A few billion times the life of the universe, or the age of the universe. So, which is a ridiculous, stupid, pointless exercise. It's not a complexity exercise anymore, you're just crazy. It's just crazy stuff. Your complexity has got to get them tight. The maximum has got to be a tight maximum. There's no point saying, oh, the complexity class of this is n factorial. Well, that's technically true. It'll be less than 10 factorial, presumably. But that doesn't help you, because you need to know whether it's going to be better than quadratic, better even maybe than n log n. Maybe you can prove that it's linear, or maybe it's logarithmic. These are really fast algorithms. They're the kinds of sandwiches you want the upper limit to be as fast as possible. I think we've still got plenty of time. And before I show you the video, just to, as if all of this isn't sort of crazy and bad enough, we don't know necessarily what we've got. That's the heading here. I think it's fascinating. How good are the bounds? And it comes back to when I sandwich it, say the upper bound on this algorithm is n factorial. Look, if I could laugh that hard, I would in your face if you said to me that your program has n factorial behaviour. I mean, that's got to be a joke, because you are telling me zero. You're saying that it will eventually finish given enough billions of years. Okay, which is a pretty empty statement. But what can we say then about the upper bounds? If you tell me something, your algorithm is x, is quadratic or cubic or something, what does that mean? Well, if we have two algorithms, one is cubic and the other one is quadratic, A and B, cubic, quadratic. We think, okay, I choose the quadratic, that's going to be faster than cubic. It's got to be faster. But do we know that for sure? Algorithm A may actually need a lot less than cubic. Cubic is the worst case behaviour. In fact, it was behaviour we couldn't easily analyse. It's a complex algorithm, very difficult to analyse, and the best estimate we could come up with was cubic. In fact, it's probably a lot faster. We don't know how much faster. That was just the best we could do. Now, the n squared algorithm, B, that turned to be out. That turned out to be really easy to analyse. So we absolutely know the n squared algorithm is what it is, n squared. Not a second slower than n squared. So we've got an algorithm A, which is something better than n cubed, and an algorithm B, which is definitely n squared. Is A faster or slower than B? On paper, it's slower, but we don't know that for sure, because that algorithm A, which was supposedly on paper n cubed, because the n cubed is a ceiling, it may actually be linear. Again, remember, this is what I'm trying to impress on you now, these complexity analysis, it's not black magic, but you're trying to contain, you're trying to learn or understand the performance of a program, and you're going to, in some sense, guess is educated guess maybe, estimate how long a program is going to take, and sometimes you can't be sure because complexities of the input mean that you can't predict exactly which paths through the program it can take. So you don't know for sure how long it's going to take, and therefore your predictions must be conservative. You can't get it wrong. You're better off saying it's n cubed and it turns out to be linear than the other way around. If you're the other way around, you should get the sack and never be employed as a software programmer. If you say your algorithm is linear and you've just been highly risk-taking and optimistic and irresponsible and say that it's, what did I say? You say that it's linear and it's actually quadratic or cubic or exponential even, you've lied. And that poor customer will, he should take you to court. Okay, that's very serious business. You can't be wrong, you must be conservative. Which means that you say, well, I'm not sure here, I'll have to say this is at least a term. And see where it comes out, and if at the end it comes out to be a quadratic or a cubic, well, that's it. I can't do better than that. And that's what it is. That ceiling is pretty loose, pretty rough. So, knowing what the ceilings are no guarantee that you've actually got a tight bound on the performance. It remains, if you know that a big O complexity is an overestimate, you really need to know the big omega as well. But the big omega has exactly the same problem. You do an estimate in the same way, you come up with a minimum time, and the question is, well, you've got to be conservative, it's going to be at least this, and it ends up, you may say, well, it's bigger than a constant, but how much bigger, I don't know. So you may have a very loose ceiling and floor on the performance. So I say here, I think, if your performance measures, your big O is exponential and your omega is constant, then basically you're saying is the asymptotic execution time of my program is somewhere between one nanosecond and billions of years. And you will fail the course. Okay, that will not impress me. You obviously want to do a lot better than that. But if you want to have a joke and you don't know what else to write, it's certainly true, what you're saying, presumably. Well, you could be wrong. If it loops forever, you'd be wrong, of course. It doesn't terminate. It's just a possibility. So here are examples of different... let's do something a bit more interesting. Let's have a quick look. I'll warn you one thing about... Well, first let's see if it plays, because I had a lot of trouble with the sound. If it doesn't play.
Is not accuracy, but Grammarly can help. This sentence is grammatically correct, but it's wordy.
Lesson 6, Big O, Big Omega, and Big Theta notation. When we speak of an algorithm's efficiency, we want to determine its scalability. That is, we want to know that when the algorithm is applied to a large data set, that it will finish relatively quickly. We can also talk about how much memory an algorithm requires, but for now we will focus on speed. We measure an algorithm's speed in terms of the growth in the number of operations relative to the input size. For the linear and binary search algorithms, for example, the input size is the number of elements that we are searching. Typically, we will use the letter n to represent an unknown input size, and we will talk about the growth in terms of n. To To formalize our ideas of growth, there are three types of bounds that we will address here: big O, big omega, and big theta. The definitions that we will use come from mathematics and are used to relate the growth in one function relative to another simpler one. Here we have the graphs of two real functions f of x and g of x, given by the gray and dashed arrows, which we use to indicate that the functions continue indefinitely. The function f of x is more complex, and we want to measure its growth in terms of the simpler function g of x. More specifically, we want to find a constant such that when we multiply it by the function g of x, it will bound the function f of x above from some point onward. Assuming that the graph of f of x does not intersect the graph of c times g of x after the point x0, we know that the graph of f of x remains in this white region for all x to the right of x0. In this case, we say that f of x is in big O of g of x. Formally, we say that f of x is in big O of g of x if there exist positive constants c and x0, such that f of x is less than or equal to c times g of x for all x greater than x0. On the other hand, we could bound the function f of x from below, like this. If such a constant exists such that c times g of x bounds f of x below from some point onward, then we say that f of x is in big omega of g of x. Formally, f of x is in big omega of g of x if there exist positive constants c and x0 such that f of x is greater than or equal to c times g of x for all x greater than or equal to x0. If there are constants such that g of x bounds the function f of x both from below and above, then we say that f of x is in big theta of g of x. Of course, the constants in this case are different, so we have labeled them c1 and c2 to clarify that. The x0 that we choose can be any value that is far enough out that f of x doesn't intersect either c1 times g of x or c2 times g of x anymore, and remains in this white area. Formally, we say that f of x is in big theta of g of x if there exist positive constants c1, c2, and x0 such that c1 times g of x is greater than or equal to f of x, which is greater than or equal to c2 times g of x for all x greater than or equal to x0. So far, we have shown what the situation looks like for general real functions. For algorithms, the input size is generally a positive integer, like the size of an array for a sorting algorithm. In this case, we can think of our f and g as functions on the positive integers. In mathematics, x is used to signify a real variable, while n is used to signify an integer variable. Like Hungarian notation in programming, this notation allows us to see more immediately what is going on, so we will use it. Using this notation, here we see the graphs.
What he does now is he goes through exactly the same for discrete values, n instead of continuous values, g of x of x. So there's some implication here that everything I've shown you before I tend to use. I think I tend to use x. I use them interchangeably, talking about continuous range, real numbers, or talking about integers, exactly the same mathematics. So he'll go through the big O notation for discrete numbers, same definition, with integers instead of reals. Go through the big omega, which is the lower bound, and the theta. Theta doesn't get used a lot, I've seen it a few times, because in some sense it's going with one step too far. The vast majority of complexity analyses are big O only. You just want the worst case, and you want a tight upper bound. If you've got that, that's 90% of the work. Having a lower bound, having some relationship with a lower bound is nice. It gives you some tightness there. It gives you an idea of how close the function is to your upper bound by limiting its lower bound. And the theta is just an embodied where you'd all put it together. Okay, so I might stop it now because it really is, that music is rather interesting. It's sort of a church organ-y music, very quiet in the background. It's almost like it's a sermon in the church style. I tend to fall asleep with it, is the way I feel about it in any case. So that's, you can listen to that anytime you like. If I can find my way back. Okay, some very simple, I'll quickly move on through this. Examples of complexity 1. If you have the Big O class 1, then the execution time does not depend on the input size. Doesn't matter what number n you give it, it'll always take the same time. When it's log n, it's a very slow increase as n increases. Whenever n doubles, the running time increases by a constant. So you double n from 100 to 200, there's a small increment in time. And you do it from 200 to 300, the same small increment in time. It crawls up, it's very slow. When it's linear, then the runtime is a function of the input. It's proportional. N log n. Whenever n doubles, the running time more than doubles, but not a lot more, as you would expect. Then n squared, of course, when n doubles, you're going to get the square of the input in execution time extra, then n cubed, 2 to the n, and n factorial. The point of all that was, what are some examples of constant algorithms? Making a cup of coffee at breakfast is an example of a constant time. You just take the same amount of time. There's no n in effect. Doesn't matter what n is, you have just one operation that you always do. Or getting the value from an array. Addressing, array indexing, A of n, I equals A of n. Doesn't matter what n is, it takes the same amount of time. Or even this program here, which is really interesting, and it's something I used in an exam some years ago. Looks horrible, and I asked for the complexity. And of course, you look at that and sort of say, well, is that exponential? That looks horrible. All those zeros. I could have put a few more zeros in it. Really a lot of zeros, 20 zeros in it. Now, the smart people, even the smart people, would say, that's constant time. I think. But you'd be nervous putting constant down. But really, there's no n anywhere. That constant may be 20 minutes. But you give it n 5 billion, it's the same 20 minutes. Because the limits of those two arrays are fixed, constant. Okay? Constant time doesn't mean fast, it just means literally fast. It means it doesn't change. It's always the same. So, in a way, it's a bit silly to say a constant time algorithm is always going to be really fast, because if it takes for n equals 1 day or 1 year, then for n equals 1,000,000, it'll still take that same day, 1 day, to execute. It just means it doesn't change with the value of n. That's all it means. It doesn't really necessarily mean fast. But, okay. So linear, reading a book is linear. Well, most people linear. You start at the start and you read to the end. It's a linear process. And if you have one loop where n is the limit of your loop, is how far you go, then of course you're going to have a linear algorithm. Of course, the bigger the n, the longer you'll be running that loop. Quadratic, when you have nested loops, both of which are n. So a simple exam question will be to give you a double loop where one of the limits is constant and the other one is n. And then you sort of see double loop, and those that think, oh, 2 loops, that must be quadratic. But you've got to see where the n's are. It's not how many loops are there, it's how many n's are there. If there are no n's at all, constant, no matter what it does. You don't care. It's constant, no n. Logarithmic, here's we have a logarithmic algorithm where we actually halve the size of the space every time. This is a search here where we look for something in the middle. Is it bigger than or smaller than in a sorted array? And if it's smaller than, then we go to the left half, and then we do the middle of again. Is it bigger or smaller? Then you go left, right, and you very quickly zero in on that element you're looking for. Then n log n is merge sort, where you effectively do something like that, but you have to merge everything later on. And then we have n factorial, where the travelling salesman's problem, where you take the brute force way of how many ways can I travel around all the states, all the cities in America, I think it was, or in the capital cities and all the states of America, how many different routes are there, and when you work it out, well, I can do that city, then that city, then that city, or I can change that by 1 and turn 2 around, and or I can change these 2 around, or I can change these 2, and you can change so many, and in the end, well, I can do n of the cities first, and then when I've done that, pick that one city, there are n minus 1 that I have to choose between after that, then I've got n minus 2 to choose after that, and that's my space. Like the sliding tile puzzle. So sliding tile puzzles. I've asked you for two examples of n factorial algorithms. Sliding tile puzzle, if you don't get that one, inclined to failure immediately. And the other one, of course, now you know, is the travelling salesman's problem, which we will be handling later on in the course. Or binary search, linear search. I don't think I want to handle that now. I want to get onto something. I want to do a little bit on recursion, that's fun. Although you're probably tired, my voice is starting to hurt a little bit. Let's just do a bit of recursion, and I'll do that binary stuff and linear stuff later. Problems that use recursion, they've got a space problem. It's a disadvantage because in recursion, you need stack space. You need to use the stack, the memory stack on the computer to run your program. So every call will require a certain amount of memory. So if your program recurses really a lot, it's really, really heavy on the computer. I've said this many times. Its efficiency, it has to sometimes, in many recursive algorithms, it actually does the same thing, it repeats the same calculation many, many, many times. And that can overwhelm and destroy the program, the performance, make it really factorial or exponential in behaviour. So recursive algorithms often are exponential, which in some sense means undoable. But think about that, undoable, you have all done Fibonacci, I would assume. That's recursive. And not one of you, I think, would say that's undoable, intractable. It's an exponential algorithm. Well, it is and it isn't. As you're going to see here, and this may really bore you, I do Fibonacci 3 ways. I do it real fast, and real slow, and then real fast again. And you can well imagine that this is all based on recursion and iteration. Okay, fast and slow, and recursion, get rid of it. So that obviously is going to change the performance. But how does it change the performance? What exactly is the performance of Fibonacci recursively? What is the complexity? And iteratively, what is the complexity? And what can you do with recursion to make it fast? It turns out that Fibonacci recursive can work. It is horrible in performance with big N. Truly horrible, except if you do a trick. And then it's fast. So you can change your algorithm from this nightmare complexity class where you will die before your program finishes of old age to one where you won't even get out of your chair and will be finished. Okay, that's the power of complexity analysis. You can actually, you understand what the program's doing and what makes it go so slow. So, Fibonacci, we know what Fibonacci is. You take the last 2 values, 0, 1, and you add them, and then you take the previous 2 values and you step up. Every time taking the n minus 2 and the n minus 1 term, you get a new value. Then you increment your n, and you keep on going till you get to the n that you want. Now, here's the standard way of doing it, the way I've done it. This little program here, I haven't done this in years, I still hope to get to GCC. I haven't tried on DCC ever. It was GCC in those days. And that little program there just initializes the Fibonacci sequence with current and prev, or prev and current, minus 1 and 1, and works from 0 and 0. All it does is it calculates the sum and then puts the sum in current and the old current in prev. So prev and current get updated all the time. They start as minus 1, 1, and they keep on getting updated by the sum and the old current. The current goes into the old prev, and the sum goes into, of course, of those 2, goes into the new current. And you go around and around in circles, as often as you like. So there's a little program which is now for us easy peasy. No problem. If I asked you to do that in the midterm or the final, to write a Fibonacci sequence iteratively, you would do that in 5 minutes, possibly. So here's just what it's doing here. I, 0, 1, 2, etc. Prev is minus 1 and 1. I said they were the initial conditions. The sum of those two gives me a sum of 0. Then the current and sum get passed to, in the next iteration, Prev and current. So you see the 1 and 0 next to current and sum become Prev and current every time. That's the repetition here. So 1, 0 goes to 1, 0 in Prev current. And then you get a new current sum, 0, 1. And 0, 1 becomes a new Prev current. And then you get a new sum, which is 1. So you have current in iteration 2. You have current 1, sum 2. They become the new Prev and current, 1, 1. You add them together, you get 2. And current and sum, 1, 2, in iteration 3 become the 1, 2 in iteration 4. And they get added, and you just go around and around in circles till you fall asleep. That's the complexity of this. Well, that little algorithm I've got there with line 4, 5, well, you can see an assignment in line 5, line 6, the loop starts at line 7, etc. I do my little analysis just like I did with linear search, and I get this, that line 5 is done once, line 6 is once, line 7 is done n plus 2 times, n plus 2. Ooh. N plus 2 and the rest is n plus 1. Why? Well, it's interesting. It's actually going to n, starting at 0. So it's n plus 1, and then it goes one more, of course, and then it jumps out. So it's n plus 2. It's a bit unusual, but that's just the way it is. I'm calculating things iteratively. There's no arrays. I'm not going to come out of any bounds or break anything. There's no mallocs. All good, clean stuff. No pointers to worry about. It's really very simple programming. So when you add those all up and you get a lot of constants multiplied by n plus some constant, which is obviously linear. So that's not really hard to do. How many times does it go through the loop in terms of n? And it's always one more sort of at the top, the for loop, then the body. So it's all really easy. Now I run it, the speed, fib it. Fib iteratively for 20, 30, 40 and 44. And you can see the user and system time is more or less 0.001. It's basically instantaneous. It doesn't make any difference the value n you give it. It is so fast, it's ridiculous. Well, okay, now use recursion. And in recursion, I've done it a little bit, you could say programming-wise, a bit sloppy with the return statements, but I want to make it really clear what the base cases are. I'm doing here programming as you would define it mathematically what's happening, algorithmically what's happening, not as you would do it in the style guide. Okay, I wouldn't have these two returns in a normal style guide program. But here we're trying to mimic the algorithm, which basically says if you've got 0 or 1, well, then you just return because the values are what they are. And then with larger values, then you have to call recursively, n minus 1 and n minus 2. So the calling program is exactly the same. And you then, well, what's it actually doing? Now this is where your eyebrows go up. You see, well, if I'm just doing fib 6, that's pretty small. Not fib 44, fib 6. You can see on the left fib 5 and fib 4. And then the next level down, fib 4 and fib 3. Oh, fib 4 was on the right. But okay, I'm doing it again apparently. And then fib 4 was fib 3 and fib 2, but that's also fib 3 and fib 2 on the right. That whole tree is repeated. Then fib 3 is fib 2, fib 1. Fib 2, fib 1 is on the right on the fib 4 tree, and is on the left in the fib 2 tree, and is on the left in the fib 3 tree, and is on the right in the fib 4. It's all over the place. The same computation is happening time and time and time and time again. When you go to 44, the vast majority of this massive tree are repeated computations. You've done this before, you do it again and yet again and again and again. It is the height of stupidity, recursion. It never remembers anything. It computes everything time and time and time for the age of the universe again. So massive repetition. Look at the nodes, number of nodes at, this is the 2 to the 0 level. Okay, so the first level is, we haven't broken it up yet, 2 to the 0. The next level down, when we have 6 and 5, is it 6 and 5, 5 and 4 I mean, we have level 1, that's 2 to the 1.